You get nervous? Yeah, that's true. I would record you. I'd set up the camera.
Hey, so I was watching your homework solution for 6.3, and you had like people in the room.
He did it for a lot of, like, a couple of videos already. Where he asked people for the...
I don't know. I guess that was the first time I noticed.
Well, in my in the conference room downstairs is where I did a lot of those videos, and students would come to my office hours, and they would just come in there, and kind of some people just wanted to sit there and.
I want to sit there if you're ever doing it anymore.
Yeah, I'm done with all the Cal 2 and Cal 3 and Cal 1, so.
You're never gonna redo your video.
When we change books, probably.
Yeah.
But even then, I don't know if I will. It's a lot of work, man.
It is a lot of work.
We know.
So
We have homework?
Tricking a girl's
that's take-home quiz.
4 hours in the middle.
Uh-oh.
I don't think I was serious.
Yeah.
3 hours.
You know what? I do have a copy if you want a copy of it.
I'll just,
I mean, you can turn it in, but you can't get full credit. All right, well, anyone else with the take-home? How'd it go?
Wasn't too bad.
Is that all right? How do you think you would have done if I would have handed those problems and you would have had an hour 40 minutes to do it? Yeah. And that's really what you got to kind of think is that next test is going to be very similar to that, right? I guess what I mean by that is, do you feel like if you got those like during a test that you would have known like how to go about each problem? You know, like this one's partial fractions, this one's, you know, that's really the main idea, that you don't want to be sitting there trying to do something you're not supposed to be doing. Okay, well, today we switch gears. We're celebrating Columbus Day today, so the destruction of North America. Yeah, I would have loved to give you a day off, but I can't do that. So, all right, we're going to talk now. This section we're covering, I'm calling it Chapter R, because there's not really a chapter in the book that talks about this. I mean, there is a chapter, but I just kind of break up this idea into my own little chapter. So your homework's going to come out of one particular section, and I'll tell you what that homework is at the end. But the ideas I'm taking from different sections. I'm just kind of summarizing it, all right? So we're done with integration, the techniques, all right? Congratulations, you made it. You made it this far. All right, so now, the motivation for all of this is the idea of the area problem, all right? So let me try and illustrate something for you. Think about way back, way back, all right, when humans were just trying to figure out, well, I guess at some point, it depends on what your beliefs are, and I'm not going to get into some big old discussion about that, but if you believe that at some point humans had to start, or had an opportunity to start thinking about the world around them instead of like where am I going to get my food and water today, and they actually had time to sit down and like think, then they started to ponder a lot of different things. And one in particular was, you know, how can we determine the area of an object? You know, how much stuff is in a flat two-dimensional object. And I think we pretty much have a rectangle. We had established the area of a rectangle very early in things. So we all know the area of a rectangle is equal to, you know, I'll call this its width, and I'll call this its height. So it's height times width, right? So can we start from that? We were at this point where we knew the area of a rectangle. And then came the question of, well, how do we find the area of something more complicated than that? So what if you had some weird shape like, I don't know. Well, maybe I should also state that we knew the area of we knew the area of a triangle also. From the area of a rectangle, you can get the area of a triangle pretty easily. So if you have a triangle like that, now notice that's not a right triangle. What's the area of a triangle? 1/2 base times height, right? 1/2 base times height. Have y'all ever seen how we get that from that triangle? Yeah. I can do it real quick, it doesn't take long. What you basically do is you like right-click copy, right? You know what that is? Right-click copy, right-click paste. And so you make a copy of this and you paste it on, and you draw it upside down, and you put it in like this. So that's that same triangle, like flipped over. You see it? Okay. And then like here's the height now, like that. So what you can do now is you can get your scissors and you can cut this, and you can take that piece and you can put it right here, like that. And now you're back to a rectangle, right? You see that? And so the area of this rectangle is base times height. But that's 2 of the triangles, so your area is 1/2 of base times height. So that's, you know, you can get the area of a triangle pretty easily from that other formula, all right? So we've got that. So what about an object that's kind of weird shaped like that? How could we find the area of this?
Break it down.
Yeah, you could probably just break it down into other things that you could measure, like you could maybe draw some lines through here, like here to here, here to here, here to here, and then you got a bunch of triangles and you can find the area of that, right? Now, I think a deeper, like more profound question was, you know, why did we need to find areas? And I think really the first motivation was once we started to realize that agriculture is how we would get our food, right? Like, so you could use the land to provide food for everybody, right? You started to get cultures, people started to live closer together, you weren't as nomadic, right? So you start to say, well, this is mine, that's yours, this is my space, that's your space. So you had, you know, we had to break up the land, right? And we had to be able to measure somehow, like, how much land do I have, right? And borders aren't always straight. Make sense? So how about something like this? I mean, because let's say you had like a river, you know, I don't know, this is a river. And let's say this was your land right here, right? So like, how do you find the area of that? You see how that becomes problematic because of the curve in there, right? You can't break that into triangles. Now, could we approximate the area? Could we get approximately what it is? Yeah, probably. We could maybe just draw a rectangle, maybe like right here, and then we could maybe approximate that one with the triangle. Who knows, right? We could get it pretty close, but we want to become more accurate. So the Chinese were the first ones to really go after this question of trying to find the area of a circle, right? Because the circle is just curved everywhere, right? So maybe there's a way that they could determine that. So the way they did it, the Chinese, is that that's not a very good circle. Let me see if I can do a different one here. That's probably a little better. Not bad, huh? All right, so if we want to find the area of this circle, then what could we do? Oh, pi r squared, right? That's it. So they had that formula? No, they didn't have that formula. Right? We know it's pi r squared, but they didn't have that formula. So here's what they did. They said, okay, we have the area that we're looking for, right? I'm going to call this area true. Okay, subscript it with true here. So the true area is something, right? And what they did first is they started to draw squares and rectangles. So they would draw a very precise circle, right? They would like get a string and they would just draw a radius very precisely, right? And then they would get straight edges and they would start measuring out and finding the area of a bunch of rectangles and squares and stuff inside this circle, right? So they would add more and, right? Measure all those areas, add them up, and that would give them an approximation, right? Now, if I added up the area of all these green shapes, would that area be bigger than this or smaller than this? Smaller, right? So they would say, okay, this area is bigger than the, how do I want to say this? I'll just call this area low, okay? It's the lower, it's smaller than this one, right? So the green would be not enough, right? So how could they get even more precise? Well, they could just draw smaller rectangles in here, smaller little, fill in all these little gaps, right? But no matter what they did, they're always going to have a little bit of error, right? They're always going to have a little bit of error in here that they can't quite get a rectangle in. Make sense? So this is always going to be strictly less than this. All right, and then what they did is they said, all right, well, let's try something else. Let's draw a big square around this. Okay, now the area of that square is too much, right? That's bigger. That would be bigger than this. So they'd find the area of that big square, and then they would start drawing rectangles on the outside, like this, and they would start subtracting these smaller rectangles from that big square, right? And that area would be what? Bigger or smaller than this? It'd be bigger, right? Because the square was bigger, and they're taking out these pieces, but they still have this error in here, right? That they're not able to take out. So they would have the area that they could calculate that would be too high, right? This measurement would be too high. But what they achieved by doing it with these two different methods, or same method, just two different approaches, is that they would start to squeeze the true area between two numbers. And the more precise, the more rectangles that they drew, the more little gaps that they filled in, the better that this would become, and this would squeeze it down and try and push this in between two numbers that were very, very close together. Does that make sense? And then they discovered, the relationship between the radius and these numbers, and they were able to approximate that the area was approximately 22 over 7. That's what they used instead of pi, and then the radius squared. So if you type 22 over 7 into your calculator, it's pretty close to pi. It's not pi, but it's close. And that's good for most calculations that need to be done, with ancient times. 22 over 7 works pretty good, all right? Now, this method of, can you see someone sitting there drawing little rectangles, right? Can you imagine what this would take, right? So there's a name for this. This is actually called the method of I think I spelled that right. Method of exhaustion. Is that right? Exhaust? Yeah. Method of exhaustion, right? It's a good name, right? You can see why this would be exhausting to do this. Maybe they would have thousands of rectangles drawn in there. So although this worked and gave us an approximation, it does not give us the true area formula. The true area formula is pi r squared. And so we still are stuck with how do we come up with this pi instead of the 22 over 7, right? And it wasn't until Riemann came along and started to use calculus that he was able to get to it, all right? Or we were able to get to it. So that's what we're going to talk about today, and that's what are called Riemann sums. I am recording, yes. Okay, yes. All right, so we had the motivation of the area problem, right? How do we come up with a formula for the area of that circle? Now, the way I showed you was using rectangles, right? Drawing a bunch of rectangles in here. But that's not the only way that you could do this. You could also use a different approach. And here's one approach you could use. You could start to put triangles in here, right? See that? I could do something like that. That would be an approximation. But then I could maybe make those triangles smaller. So how about I do that? I start using all those little triangles. Now, do you see? It's probably hard for you to see here. Let me get this down here. Yeah, there. I think it's a little more pronounced there. You still have some yellow in here, right? Because these are curved and these are straight lines. So you're going to have some error there. But that's a pretty good approach, right? And the more triangles you have, the better your approximation. Do you agree with that? So if I were to somehow, I want you to think of this two ways. I can make the size of the triangle smaller, which makes this angle smaller, right? So if I make the angle smaller, like that, right? Then I have to have more triangles in there, yes? And the idea here is that if you want to have the true area of this circle, what you need to do is have an infinite number of triangles, right? I mean, does that idea make sense? But what's wrong with that idea? What if I tell you there's an infinite number of triangles in here? What about the angle? Okay, so the more triangles I have, the smaller the angle gets, right? Infinitely smaller. But if there's an infinite number of triangles, then how big is the angle? It's got to be going to 0, right? And if you have a triangle with an angle of 0, you can't have area, can you?
That's not a triangle.
Because it's not a triangle, right? That would be like a straight line. So it'd be like, okay, here's one side of my triangle. Instead of putting the other side like this, you're going to say it's the same side, right? The same side. So you can't marry. Well, you can't marry. What the hell? Okay, let me have some more of this. You can't measure, right, the area of a line. A line has no area. All right, so we start to get to a point that it stops making sense, the area, right? But calculus supplies us with something very important, and that's the idea of the limit. And so what we ask ourselves is, all right, we don't say we're going to put an infinite number of triangles in here. We're going to say what would happen if we let the number of triangles approach infinity, right? And that's what the limit always let us do. Approach something without actually getting there, right? Limit as x approaches 2. Well, that doesn't mean x is 2, that means x is getting close to 2. And we saw with limits in Cal 1 that as we did limits, we would get numerical answers. Even though at a certain value, we may have undefined or 0 over 0 or something like that, as we approached, we could still get a nice number. And that's exactly what's going to happen here. All right? So we're going to do some sort of limit. But without the limit, you can't do it. All right? Still make sense? Okay. Let me take this back. All right. So we don't need that. I'm not going to do that. I decided I wasn't. All right. So Riemann started this whole thing out with not looking at the circle, but looking at functions in general. All right. So let's say we have a function. Can you all see this blue curve here? All right. So let's say we have that function. I'm going to draw it over here also. Say we have this function goes like this. All right. Let's just stop it here. So there's like this right endpoint, and then this would be like the left endpoint. If we want to find the area in here, what we could do is approximate it with rectangles. So in this particular case, as you can see, I have 5 rectangles that I've put in here, right? And if we added up the area of each of these rectangles, added them up, we would have an approximation. That approximation would be too much though, right? It would be more than this area. Now, I want you to notice something about the way that this is drawn. I have 5 rectangles, right? Do you see that they all have the same width? Right, whatever this is, I'm going to call that W. Do you all see that they're all the same width? Yes? So each rectangle is the same width. That's important because we're about to create a formula. I just want to make sure we're clear on that. Now also, how are they getting the heights of each of these rectangles? And you have to remember that this is a function that we would know. Okay, so somebody has already given us a function. Maybe it's x squared plus 1. Maybe it's sine x, natural log x. Whatever it is, we've got a function that's been provided to us. So there it is, and we're trying to find the area under it. So how is this height of this first rectangle determined? What does it look like we did? Like, why didn't I stop here? Yeah, we just took the coordinate. We took the y coordinate of that point, right? So it's kind of like what we did is we said, all right, to figure out what the first rectangle, what I'm going to do is I'm going to walk out Like this is 1, you can't tell, but that's 1, right? It said, okay, start at 1, which is the left side where we're going to begin, and walk out by this width, whatever the width is, right? Walk out by that much. So this point right here would be 1 plus w, wouldn't it? And then take 1 plus w, plug it into the function. And that would give you the y-coordinate, yes? So this height right here is f of 1 plus w. Now I'm gonna go through this again, all right? I just want to, with this picture, everyone see that. All right, so for rectangle 2, what would be the x-coordinate here? You could say 1 plus 2w, couldn't you? Yeah. Right? Because it's like you start at 1, but instead of walking out just 1w, you go 2. So this would be 1 plus 2w. And then the height of that would be, f of 1 plus 2w. And so on and so forth, right? Now, that would give us an approximation. Like I said, this would be too much, though, right? That would not, that'd be a pretty bad approximation. So how could I get a better approximation? More rectangles, right? Or smaller width rectangles. So I have an animation that'll do this better for us. First of all, let me change this. Yeah. Thought I had that same graph. Can I use that one? Is that all right? Okay, so that's a slightly different graph, but if I wanted to approximate the area under that graph, then what I could do is, well, that's one rectangle. You see that that's one rectangle? Yes. I just went all the way to the end, went up and over. There, that's not a very good one. Also, I want you to notice, if you can here, this is the true area, okay, 5.3643, and this is my approximate area. Okay, I know you may not be able to see that back there, but watch what happens as I add more rectangles. So here's 2 rectangles. Look at my estimated area is now 6.3. If I do 3 rectangles, 4, 5, 6, 7, 8, 9, 10, right? So what, we're up here, let's go 25 rectangles. If I get 25 rectangles in there, the true area is 5.36. My estimated area is 5.45. So I'm getting there, right? I just need more rectangles. More and more and more and more. Let's see, 5.4. It's actually going pretty slow now. It's not. Okay, so 70 rectangles. All right, and I'm within, looks like I'm within 3/100ths of the true area, right? That's only 70. I could easily throw 1,000 in there, right? I mean, if I did 1,000, they would each have some width, right? It would be a very small W, but it would be something, right? But then I'd have to actually add these up, right? So even if I did this, right, adding up 70 areas would be a pain in the butt, wouldn't it? Okay, or 1,000 areas. And that's what, with the limit, we want to basically let that go to infinity, which is nuts, right? But that's the idea, right? That's the idea, is that if we could somehow add these up, the more rectangles we have, the better our approximation is. Now, okay, so we're not going to worry about this right now. All right, so we are now going to generate a formula, all right? We are going to go through this the way that Riemann went through this, kind of. See if we can't generate a formula. Okay, we're going to start off with the problem, and that is we have a function. We're going to start it out somewhere, okay? So we're going to go to the point on the function, whatever it is, and let's start arbitrarily. So let's call this a. And then the function does whatever it does. And let's say we're going to stop this here at b. All right? Now I want to start putting rectangles in here. And I don't want to put 10 rectangles. I can't put an infinite number of rectangles because I can't, what does that mean, right? So what I'm going to do is I'm going to start by putting n rectangles in there, right? N. Now I'm not going to tell you what n is, but let's assume that n is greater than 1, all right? So if I started drawing n rectangles in here, you know, my first rectangle, for the sake of space, I'm just going to make it so you can see it. It would start here at this point. It would go up to the function, go over, and then come back down, right? That would be my first rectangle. And then I would have my second rectangle would go up, over, down, and then maybe my third rectangle up, over, down, so on and so forth. So we'll call this rectangle 1, rectangle 2, rectangle 3. And then at the very end, I would have my nth rectangle. That's an n, okay? What I'd like us to do now is see if we can't come up with a formula for the area of each one of those rectangles. And when we do it, something cool is going to happen. All right, so let me put down the area of this, the total area, okay, underneath this blue curve is approximately rectangle 1 plus rectangle 2 plus rectangle 3 plus all the way till I get out to rectangle n. Do y'all agree with that? So when I say R1, R2, R3, I'm talking about the area of that rectangle, all right? So if I add up those areas, that's approximately the true area. So what's the area of rectangle 1? And remember, this function is, let's call this function in blue. Let's just call it f, all right? So what's the area of rectangle 1? So width times height, yes? Width times height? We need to figure out the width of that rectangle. Let's start with the width, all right? And I think to do this, what I like to do to help students see this is I like to do it like another picture over here with actual numbers, because I think it helps for you to get the formula if you see it like written in a specific case. Let's say this was 2. And let's say we stopped here at, I don't know, 6, all right? And imagine that we had, let's just say, 10 rectangles in this, right? What if we had 10 rectangles here? How wide would each one be?
4 divided by 10.
What is that?
4 divided by 10.
4 divided by 10. So where is that coming from? Well, we know the distance from here to here is what? 4, right? That's 4. And you're going to divide it into 10 rectangles. So you've got, 1, 2, 3, 4, 5, 6, 7, 8, 9. That's 10 rectangles in there. So each one of these has to have the same width. So it's going to be that total distance 4 divided by the number of rectangles, so 4/10. So each one of these, the width of each one of those is 4 divided by 10. Now, where did you get the 4 from? The distance between these two, which is really the 6 minus the 2, right? Over the 10? Yes? So for each one of these rectangles, every single one of these, how could I come up with a formula for the width of each one? B minus A over n, right? That's how wide each one is. So the distance from here to here is B minus A, this one minus this one. And then the total number of rectangles we have is n. So this right here, this width, I'm going to say the width of that, I'm going to write the word width, is equal to B minus A over n for each and every rectangle, right? Yes? Now, what about the height? So I don't think we need this picture anymore, so can I dump this? Okay. Well, maybe I did. Well, we're about to see. We're about to see. So right now, what I'm doing is on the side here, I'm trying to find the area of rectangle 1. And you said that that's going to be the width of it, which is B minus A over n, width times the height. What's that?
Why?
Why? Did you say why?
Yeah, why?
Why?
Why? Not like.
Well, because we're trying to find the height. Yes, it's the y coordinate, right? It's the y, but where? But where?
In between R1.
It's this point right here, right? That point right there. What is that point? See, maybe I did need that picture. Let me put it up here again. This was 2. This was 6. You said that the width of each one of those was 4/10. I'll leave it as 4/10. I realize we can reduce that. This goes like that. So what would that point right here be that we went up in here? What would this one be right here?
The function composed of 4/10.
It would be the function, right? But then what's the coordinate of this point? You're close. Not 4/10 though.
2 plus.
2 plus 4/10, right? You have to start at 2 and then move over by 4/10, don't you? So this would be 2 plus 4/10. So for us, this point right here is A plus that jump, right? And that gets plugged into the function. So area of rectangle 1 is the width of it times the height, which is f of A plus B minus A over N. Did y'all see that? You'll see where that comes from? Okay. That's the area of rectangle 1. What's the area of rectangle 2? Well, how wide is rectangle 2? How wide is it? Same width, right? B minus A over N. And then times f of, yeah, so now what we do is we want to get to this point, right? So we start, if we were to start out at A again, we would start at A and we wouldn't jump over by B minus A over N, we would jump twice, wouldn't we? So 2 of those. So why don't we put A plus, and I'm actually going to do this jump in a different color. 2 times B minus A over N. And up here, next to this one, I'm going to put a 1, even though we didn't need it. But you're going to see that that's the only thing that's going to change in our formula now, right? So what is R sub 3? Well, still B minus A over N. F of A plus, this time we're going to jump over 3 of them, right? So 1, 2, 3, that'll put us on the right side there. So 3 times B minus A over N. What you have to keep in mind is that if we're going to be trying to find the area under a function, we're going to know the function, right? We're going to know the function, it's going to be given to us. We're going to know A and B because we're going to be looking between 2 points. We're going to have to always say, hey, what's the area between, let's say, 2 and 6? So we're going to know what the function is, we're going to know what B is, we're going to know what A is, right? And then the number of rectangles we use, well, that'll be, we could use 10 or 1,000, whatever it is. What I'm getting at is this is all going to be a number, right? This plus 3 of these, that's all a number. So you're just taking a number and multiplying it times a function plugged into the number. So we can get these, right? We can actually calculate these. All right, do I need to write what the 4th one will be? No, right? But let's see if we can get the nth one. The nth rectangle will be, well, the same width, B minus A over N, F of
A plus N.
A plus N, oops, I should do that in blue again, N times B minus A over N. And there's something kind of cool about that. Do y'all see it? Yeah, if you cancel these n's, then you get A plus B minus A, which is F of B. Right? F of B, and isn't that the right endpoint? That's B, right? So F of B. So it makes sense, like our formula looks like it works, right? Now, it actually turns out that when you do these Riemann sums, like I looked at this rectangle and I picked the right endpoint, right? And I went up and over, and then I picked this rectangle, I picked the right endpoint and went up and over. You can actually do this by doing the left endpoints also. The formula changes. But you get like left endpoints instead of right endpoints, or you could do any point inside the rectangle and go up and then create your height. The reason it doesn't matter, you always get the same answer, is because these rectangles start to smash down when we let n go to infinity. And so it doesn't matter if you're picking the left endpoint or right endpoint, they're all going to become the same point once you take a limit. I'm just throwing that in there, all right? So, yeah, we've got a pattern here, don't we? We've got a pattern. So I think we have a formula for this approximation. But this notation right here, this notation, although it makes sense, like R1 plus R2 plus R3, we prefer to use a different notation. Whenever you have a bunch of things to add up, we use something else. Summations. So we're going to take a slight detour here to make sure that you are familiar with sigma notation. Now you should have covered this a little bit in 1414, or at some point before this. We use this Greek letter sigma, which is the capital S, the capital Greek letter S. And we use that in mathematics to create a shorthand notation for addition. So here's how this works. If I want to rewrite this right here, all right, in a way that it's more condensed, then here's what I could write. I'm going to rewrite this whole thing. The area is approximately equal to summation, and then what I'm going to put here is R sub I, all right? So notice that the only thing changing in this formula, the only thing changing are these subscripts, right? So I'm going to call that subscript I. And then on this notation, I put I right here equals 1, and then here I put n. And what this means is the sigma tells you, look, we're going to start adding things up, all right? We're going to add things up. Now, what's the first thing we add up? Well, what we do is we start by replacing our I with 1. So I'm going to say this equals, I start by taking this expression, replacing I with 1. So I replace that with 1. Done, right? Then you say plus, now we let this thing, which is called the index, we let it go up by 1. So now it's at 2. So we replace I with 2. And then we say plus, and we keep going. We let I go up again, R sub 3, plus, and then when do we stop? Well, this tells you where to stop. Okay, so if this said 10, we would stop at 10. If this said 100, we'd stop at 100. If it says n, then we say dot, 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 plus R sub n.
So it's like a for statement for index.
Yep. It's like in a for statement in coding, you usually have, well, sometimes you can just do like I plus, and that automatically goes up by 1, or I plus plus.
I minus minus.
Yeah, so depending on what you're coding in, that can be different. So, all right. How many of you have seen sigma notation? I just want to know how much time I really need to spend on it. Everyone's pretty much seen it? Okay, if you haven't and you're uncomfortable with it, just come by my office. We can work through some stuff. It's not super important right now. When we get to chapter 8, we're going to be using sigma notation a lot. All right? So we'll be able to get back into this. Okay, well, we have a condensed way of writing this, right? And we said that when you actually look at R1, R2, R3, Rn, all of them are identical, right? They're all identical, with the exception that this changes from a 1, then to a 2, then to a 3, then to a, it keeps going until we stop at n, right? So I can actually write this formula in sigma notation. So here's what it would look like. I'm going to erase these. So the area is approximately equal to the sum index I equals 1 to n of those expressions. So all of those expressions had one thing in common, right? They all had that b minus a over n, didn't they? That was the width. I'm actually going to slap that to the back. B minus a over n. Now in front, and I don't think I gave myself enough room, but I'll try. We have the height, which was f of a plus. Now the thing that was changing in there was that 1, 2, 3, 4, right? So in my formula, that's going to be my I. I, and then it was times b minus a over n, right? And that's what got plugged into the function. Does that make sense? You let I start at 1, and you're going to replace that with the 1, and that's going to give you the area of that first rectangle. Then you let I be 2, and it's going to give you the area of the second rectangle. Now, we'd still have to actually compute this, right? Yeah. Okay, and that would be very problematic if n was big. Right? You'd be sit there grinding away at that. But all I want you to realize is that the formula comes from a pretty straightforward geometric picture, yes? All right. So those are Riemann sums, and sometimes in calculus classes we actually compute Riemann sums by hand. So they'll be like, hey, here's a function, look at it between 2 and 6, cut it into 15 rectangles, calculate the approximated area. And it's very tedious, and you have to use special summation formulas and all this stuff. I'm not going to do that, all right? Just because of time, we're not going to do that. What we're going to do is use a major result, and that is this. The true area, all right? The true area is equal to, so no longer approximately, the true area underneath that curve between A and B is just one small tweak to this. The limit as n goes to infinity of this summation, I equals 1 to n of f of a plus I times b minus a over n times b minus a over n. Okay, so this is a major result. Major result. That if you want the true area, all you have to do is, this is basically saying let the number of rectangles you have go to infinity, right? Let it go to infinity. But you have to see, though, that if you do that, you're going to have a problem. I mean, this is basically letting those rectangles become lines, right? Because what happens to this width right here? B minus a is a number, right? Over n. If n's going to go to infinity, that's going to go to 0, right? But just because one thing goes to 0, we don't know what that goes to because we don't know the function. We've seen before in calculus that even if you have something that's like infinity times 0, right? That can still go to a number, right? In a limit. So even though this goes to 0, it does not mean that this sum is 0, right? It can still make sense. All right, so that's the true area. Now, I want you to notice something about this. Well, maybe I should tell you, trying to think of how let me give you the theorem first. All right. So, you may or may not be aware of this, but in college algebra or in algebra, there's what's called the fundamental theorem of algebra. Y'all ever talk about that in pre-cal? Or I know in my pre-cal I don't talk about it. In 1414, fundamental theorem of algebra. Yeah. Basically, it has to do with polynomial functions, in that all polynomial functions have to have, like a polynomial function of degree n has to have n complex zeros. Okay, it's not relevant, all right? All I'm getting at is this. Algebra has a fundamental theorem, all right? Calculus also has a fundamental theorem. In the fundamental theorem of calculus, there's two versions of it, and the one I'm about to give you is the one that we're going to use. Now this theorem, what this theorem is going to do is it's going to connect the area underneath the curve to the antiderivative, which is what we've been doing, antiderivatives, right? So this theorem is actually going to give us a connection between those two, and I'm not going to prove the theorem in class, so you're just going to have to take it on faith, all right? If you want to see a proof of it, I can go through it in my office, but it's a little involved. You have to have some background with how you prove things, like how do you do proofs. So here it is, all right? The fundamental theorem of algebra, calculus. Is it fundamental or E? It's A, right? Okay, fundamental theorem of calculus. All right. Well, like I said, there's two versions of this. I'm going to give you the version that corresponds with what we're doing here. Now, I'm going to do it in words first. It says this. Given a function f on a closed interval ab. So basically, if you're given this picture of a function between a and b, all right, then the area under f between, no, you know what, get rid of under. Just say the area between f and the x-axis is the following. Capital F of B minus capital F of A. That's the theorem. Now this theorem is actually just completely mind-blowing. Because what this is saying is that if you're looking at a function little f, right, and you're trying to find the area under it, what you have to do is calculate this, which is what? What is capital F related to little f? The antiderivative. Remember when we were talking about antiderivatives, right? Way back in the day, in the very beginning. Said, given a little function f, the antiderivative capital F, right? Okay, so this should be completely nuts to you to think that if you want to find this area, all you have to do is find the antiderivative of this function and then just plug this point into that function and then plug that point into that function and subtract the answers.
Is that a definite integral?
That's what a definite integral is, yes. All right? Does that not bother you, blow your mind? Is that not nuts that it would be that easy to find the area underneath a curve? That's why it's a fundamental theorem. I mean, that's a major result. No Riemann sums necessary. You don't have to do any Riemann sums. So a lot of calculus classes, they show students how to do Riemann sums to kind of torture them a little bit and see like, whoa, this requires a lot of work. And then they say, oh, but here's the fundamental theorem. And then they're like, oh, crap, everything that just took me like half an hour to do is going to take me like 30 seconds. All right? So I'm sparing us that, but I want you to appreciate that this theorem is taking place of this computation. All right? Now, so when this theorem was put together, we needed to come up with some sort of notation for this, right? So do you remember when we started talking about antiderivatives, I showed you the notation, the integral sign and all that? I said later on we'll talk about where that came from. Okay, so here's where the notation comes from. Take a look at this right here, right? All right, what we have here is basically the height of the function, right? That's the height of the function. So it's essentially the function evaluated at some point, right? Now those points are going to change, but it's basically some point. So it's an x coordinate there, right? Yes? And then this right here, this is the width of each rectangle, right? So you could say, like, when you go back and you look at those rectangles we drew, like here was the function, you had all those rectangles in here, you could say that this was somehow like counting these little jumps, right? Those little jumps. Each one of those jumps was how much our x changed by, right? Change in x, what symbol do we use for change in x, like in physics and stuff like that? Delta x, right? Y'all seen that delta x before? That's change in x. But see, the thing is, we're going to take a limit, and those little changes in x are going to become like infinitesimally small, right? So when they become infinitesimal, instead of using delta x, we use dx. So dx is this piece, right? This is your change in x, but your infinitesimal change in x. Do you see where I'm headed with this? Now this right here is very special. That would just be a sum, right? But it's the limit of a sum. And so we have a special notation for that. Okay? You see it? So this right here is the antiderivative, right? This is, I told you, this is what's going to tell us antiderivative, but really, it's coming from the idea of this symbol is from a limit of a sum. This right here is, well, a function evaluated at some point. Then here, this is like our dx. All right? So when you look at this integral now, I want you to see it a different way. I want you to see that this is adding up, right? This is adding up a bunch of things. What it's adding up is the function's height times the function's width. Or sorry, times the rectangle's width. Sorry, not the function's width. Height times width. Got it? Because we're going to start doing some weird stuff with this. Like we're going to take this this right here, and we're going to just like rotate it around the x-axis, like swing it around, make it three-dimensional. It's going to be a solid. We're going to try and find its volume. And when we do that, our formula, this is going to have to change, because this adds up widths and heights. We're going to have to be adding up some other things, so our formula is going to change, right? Now, we know that notation, right? We know this notation to mean just find the general antiderivative, right? Then plus c at the end. Yes? That's not an area, is it? So we need to add one more thing to this notation to let everyone know we are not talking about just finding the antiderivative, that we're actually finding the area under the curve. So what we add are two little things. We just put here on the bottom of the integral sign an a and a b, and those are two numbers, right? And those numbers are these numbers. And that lets everybody know, hey, look, we're not looking for a general antiderivative plus c anymore. We're actually finding the exact area underneath this curve between those 2 points on the x-axis. So this has a name, right? And that's called a definite integral. So I'm just going to kind of recap that here. This right here, this notation, is called a definite integral. Okay? These two numbers here, this right here, is called the lower limit of integration. And this one right here is called the upper limit of integration. They call it the definite integral because your answer is numerical, right? Your answer should be a number, right? And isn't that a definite answer? What do we call it when these aren't here? When these limits of integration are not here, what type of integral do we call that? Indefinite, right? And it's called indefinite because there's a plus c, right? And plus c means there's an infinite number of functions that would satisfy that. So you're kind of indefinite. You don't really know exactly what the answer is. So this right here, indefinite.
So this removes the plus c?
Yes. Because you're going to get an actual numerical answer. So that's what I was going to put here. Definite integral, the answer is a number. Now we're also going to find out later that it could be that it's infinity, all right? But for now, I'm just going to say a number. Indefinite integral is going to be a function plus c, right? So the difference between a definite integral and an indefinite integral is monumental, right? These are like apples and oranges. This is going to give you a numerical answer. This is going to give you a function answer. So it's kind of important to see that if you look at the order in which things happened, this notation came before this notation, all right? We started with this, okay? We started with this. Well, we started with this. And then from this notation, we created this notation. Then we said, hey, look, to do this, we have to find an antiderivative, right? So we'll just use this notation without the numbers to let everyone know, hey, go find the antiderivative, all right? But none of this notation works if we don't have the fundamental theorem of calculus. All right, so let me, one last thing, and then we're going to do some problems. And I'm not going to leave you hanging. We're going to find the area of a circle today is pi r squared. We're going to derive the formula ourselves. All right? You have a question? Yes.
Did Riemann ever see like the completed fundamental theorem?
Oh yeah.
So
Yes.
he saw it
Yes.
live. Was
Yep.
he like kind of dissatisfied that
No.
he did all that work and then it was?
Oh no! I don't think so. No, I don't think so. Have y'all heard of the Riemann hypothesis? The Riemann hypothesis?
The one that hasn't been proven yet?
Yeah.
Yeah, that one.
So Riemann has a very famous problem. It's one. There's a couple of $1 million questions. Like if you can solve them, you get $1 million. And one of the top one on the list, I believe, is the Riemann hypothesis. Like it's the one that's everyone's trying to get, and it's very elusive and very difficult. And someone in my other class told me that that had been proven. But then he, what, who said that?
He's not here.
Yeah, but I think he retracted that after like the next class. He said that maybe it hadn't. But either way, so Riemann has a lot of contributions to mathematics, not just the Riemann sums. All right. Okay, so here we go.
Are you going to tell us about the $1 million question?
Go look it up. It's complicated. You have to understand the question first, and just understanding the question is kind of complicated because it's okay. Well, I can give you just a very basic idea. Okay, let's say we had the function like f of x equals x squared minus 4, and I asked you to find the zeros of that function. So what you'd be doing is finding the values of x which make that function 0, right? So 2 and -2 would work, right? Well, the Riemann hypothesis has to do with the zeros of a complex valued function, which the complex, once we start talking about complex numbers, then this variable can be an imaginary number also. So he hypothesized that all of the solutions to a particular, all of the zeros of a particular function lie on a specific vertical line. And we've had computers check billions of points on that line, and all of them do. They're all zeros. But that's not a proof. To prove something's true always, you have to prove it. You can't test. Like, it's kind of like if you've woken up for the past, I don't know, 10,000 days and the sun has come up every day, does that mean the sun's going to come up tomorrow? You know what I'm saying? Like, that's something happening a billion times in a row is no evidence that it's going to happen again, right? That's not a proof. So just because we've tested all the zeros and haven't had any contradictions, then that's not a proof. Does that make sense? Like so we don't have a direct proof for it. And that's what we're looking for.
Can you show the graph again? It was like just all over the place.
The graph of what?
The hypothesis lessons.
I don't know. I think I may have. It's all based on what's called the Riemann zeta function. So you can Google Riemann zeta function and you can look at that. And
Oh yeah.
so,
That was crazy.
yeah. So, all right. Yeah, it's beyond anything I want to do in here. But it's cool. I mean, it's cool, but it's... All right, fundamental theorem of calculus. Fundamental theorem of calculus, all right? I'm shortening that thing. Here it is. So I'm gonna show us this in a nice condensed form. All right, here we go. We know from now on, when we see this, that means the area under the curve between that closed interval AB, right? This, we know by the fundamental theorem of calculus. I want you to leave a space in here in the middle, is capital F of B minus capital F of A, right? That's what we know. All right, now I've left a space in the middle because the standard way that we write this middle piece is just to help us when we're actually computing one of these. This intermediate step before we go from here directly to here. And that's this. We're going to put capital F of X, and then we're going to put a bar here, and we're going to put A and B here. What that intermediate step does is it allows us, before we go from here to here, it gives us an opportunity to actually write down what the antiderivative is. And you'll see this when I actually do a problem, all right? But that's, if you're going to take one thing away from today, that's the thing you want to take away right there. All right, so let's do an example, all right? Let's do an example. The first example is going to be an example that's just going to help set our minds at ease that this works, okay? So what I'm going to do is I'm going to take the function f of x equals x, and I want to do it on the interval 1, 3. Okay. I want us to find the area. Under f. When I say under f, I mean under it to the x-axis, all right? So I'm going to draw it first, okay? I mean, we could go right to this, but I want us to verify that this is actually going to work. So f of x equals x. I hope you're all comfortable with the idea that this is just the diagonal function like this, right? Okay, so if we start at 1 and end at 3, like here's 1, let's go, here's 2, here's 3, then we're trying to find the area under there, right? Can we do this without calculus? Sure, right? We could break this up